Assalamu alaikum. Hello friends. In this video, we will learn Young's double slit experiment and its derivations. In derivations, we have equation for part difference and equation for the position of dark and bright fringes. Alongside, we also learn constructive and destructive interferences. So let's get started. Young's double slit experiment was first performed by Thomas Young in 1801. This is the schematic diagram of Young's double slit experiment. In the experiment, we have first barrier which has one slit, and we called it as slit 1. And the second barrier which has two slits, slit 2 and slit 3. This is the viewing screen where different patterns of dark and bright fringes appear, and this is the source of light. For this experiment, we assume that light is wave in nature and we use monochromatic light. A monochromatic light is a light which has a single wavelength. These are the waves of the incoming light. The red line shows the crest and the blue line shows the troughs of the waves. The light is first allowed to pass from first barrier and then it allowed to pass from second barrier. After passing second barrier, the light waves interfere because these two slits act as two different sources of light. These slits are very near, so the light waves interfere each other. Due to this interference of light waves, we see different patterns of dark and bright fringes on the screen. Now the question might raise that why these fringes appear on the screen. To understand the answer, let's first clear the concept of constructive and destructive interferences. Constructive interference. A constructive interference is basically the collision of waves having same phase. Crest and troughs are called the face of a wave. This is wave 1, this is wave 2. These are two different waves coming from two different sources. The upper part of the wave are called crest and the lower part of the wave is called trough. Now, in constructive interference, crest of one wave collide with the crest of another wave. Similarly, trough of one wave collides with the trough of another wave. It means we have same phase interference. As a result, we got a new wave which is bigger in amplitude. This is the resultant wave which has a bigger amplitude, and this is the result of constructive interference, a new bigger wave. Unlikely destructive interference. A destructive interference is basically the collision of waves having different phase. In destructive interference, the crest of one wave collide with the trough of another wave, and the trough of another wave collides with the crest of another wave. So both waves cancel each other. As a result, we got no wave. This is the destructive interference. Now let's return to our schematic diagram. Whenever there is constructive interference, we see a bright fringe on the screen. Whenever there is destructive interference, we see a dark fringe on the screen. Or more verbosely, whenever crest collide with crest or trough collides with troughs, we got constructive interference on the screen or the bright fringe. However, when crest collides with trough, we got a dark fringe on the screen. C is the central point. In simple words, you can say it is normal or a central axis. At point C, we always have a bright fringe because at point C, we always have a constructive interference. See at this point where two troughs are meeting. And at this point, we got a dark fringe because there are different phase interaction or interference. So this is basically the Young's double slit experiment. Now let's proceed to our derivations. understand a derivation first, we should understand the path difference. Two waves from two different sources travel different distances and reach at the same point. The difference between the two distances is called path difference. Now, this is the ray diagram of the experiment. This is the second barrier. This is our viewing screen, and this is the ray of light coming from source 1. This is the ray of light coming from source 2. This distance from A to B is a small d, and the distance between the second barrier and the viewing screen is represented by capital D. Now, according to the figure, the path difference is Bn. Path difference is Bp, since path difference is the difference between the distances traveled by the two waves. So Bp is the distance minus AP equals Bn, this distance Bn. Because the ray 2, let's name it as, for the sake of simplicity, this is ray 1, this is ray 2. The ray 2 travels Bn times more than ray 1. So the difference is Bn. Path difference is Bn. Now consider the triangle ABN. Triangle ABN. This is the triangle. This is the small theta as I'm showing the figure. Okay. So sine theta is equals to Bn upon D. We know that sine theta is equals to perpendicular upon hypotenuse. So this is our theta. Adjacent to theta is base. An is the base. Opposite to theta is perpendicular. Bn is our perpendicular. And this is hypotenuse AB. Since AB is exactly equals to small d, so we write sine theta is equals to Bn over small d. By doing simple maths, we can transform the equation as Bn equals to d sine theta. Now we need to calculate this x. This x is basically the distance of nth order of fringe from the central axis. Okay, at point P we assume that there is a constructive interference, and at point P we have a bright fringe. So this x is the distance of nth order of fringe from the central axis. Okay. Since by using the trigonometric identity, we know that when theta is very small, sine theta is equals to tan theta. Now I draw this line. This is the normal. This dotted line is the normal, and this is the small l I represent. So sine theta is equals to tan theta by using the trigonometric identity. Let's consider a triangle PLC. Now we need to calculate this x. That is why we are dissecting the figure into two triangles, into two right angle triangles. One is this. Okay, so PLC, this is our another right triangle we use. From this right triangle, this is our 90-degree angle. Tan theta is equals to PC, since tan theta is equals to perpendicular upon base. So tan theta is equals to PC upon LC. PC upon LC. PC is equals to x. The distance PC can be easily replaced by x, and the distance LC is capital D. So tan theta equals to x over capital D. Now according to the transitive property, sine theta is equals to xt, because sine theta is equals to tan theta, and we can also write this is equals to tan theta. You can also write it that trigonometric identity. So the path difference would be, now our path difference equation would become Bn equals to d small d into x over capital D. We have derived the equation for path difference. This is the equation. Now since we need to calculate this distance, since we need to calculate the position of dark and bright fringes, we need to separate this x, because x is a distance. Doing simple mathematics, this capital D which is in the division goes in multiplication, and this d which is in multiplication goes in division. So the equation becomes x equals to bn into capital D over small d. This is our equation A. Remember the equation. Okay, so this is our equation A. We need to calculate the equation for bright fringe. For bright fringes, the path difference is equals to m lambda. It is always, this is the obvious thing. Whenever the path difference is m lambda, there must be a constructive interference. M can be any whole number. It may be 0, 1, 2, 3 or any. Path difference can be measured in meters, but in generally, for the sake of simplicity in physics, we measured it in lambda. So therefore, the path difference of bright fringes is m lambda. So the position of bright fringe is x equals to m lambda times d over capital D over small d. It shows that when x is equals to this, we have a bright fringe. By this equation, we can predict the position of bright fringe as well. Equation of dark fringe. For dark fringe, the path difference is equals to m lambda plus 1 upon 2 lambda. This is also obvious fact. Whenever the path difference is m lambda plus 1 upon 2 lambda, we always have a destructive interference. As a result, we see a dark fringe on the screen. Therefore, the path difference for the dark fringes is m plus 1 upon 2 whole is multiplied by lambda. And the position of dark fringes on the screen is m plus 1 upon 2 lambda whole is multiplied by lambda multiplied by capital D over small d. So in nutshell, this equation shows the path difference. This equation shows the bright fringes from central axis, position of bright fringes, or you can say the distance of bright fringes from the central axis. And this equation shows the distance or position of the dark fringes from the central axis. There are a lot more details that can be explained. If you are interested, then you can book a session for yourself, and please also go through the presentation for complete notes of this topic. Also visit my page Online Learning Pakistan. Also visit my Facebook page Online Learning Pakistan. And if you have any questions or queries regarding this video tutorial, you can ask me at online_learning at email@outlook.com. Thank you for watching the video.